Hello everyone, welcome back to my organic chemistry mini lecture. Our topic today will be resonance structures. When we draw Lewis structure, sometimes we can draw more than one correct structure, and that called resonance structure. In organic chemistry, the resonance is also called a delocalization. That means some of the pi electrons or lone pair electrons can delocalize to several atoms, and in that case, the structure will be more stable. The extra stability because of this resonance, it's called resonance energy or delocalization energy. So resonance is also called a delocalization. Okay. And today I will show you how to draw the resonance structure. I will use some examples. For example, this first example is carbonate. Carbonate is a polyatomic anion. That's the formula. Okay, and if you draw the Lewis structure shown here, so carbon is central atom. And the single rule of the resonance structure will be you need always only move either lone pair electrons or pi electrons. You cannot move like a sigma bond electrons, no. And also you can only move that to sp or sp2 hybrid atoms. You cannot move to sp3. For example, here we have lone pairs on the oxygen here. And this carbon is sp2 carbon. So that's why this lone pair electron can push to here. This carbon can accept it. And also at the same time, you have to break that pi bond to keep this carbon has 4 bonds. Okay, so that's how you draw the arrow pushing, and then break that pi bond. So you can draw this resonance. And this resonance can also draw another resonance from here, pushing this lone pair of this oxygen, push back. This carbon again is sp2, so this can push to here, form the pi bond, and break this pi bond. And then you can draw the third resonance structure. And the real structure of the carbonate is actually the hybrid of these 3 resonance. So if you look at the bond here between the carbon and this oxygen, it could be single bond or double bond. So average is the bond between single bond and double bond. So same thing as here. This bond could be double bond, could be single bond. So the average is between single and double. And this bond is also when you average, and that's between single bond, double bond. And all the oxygen, they have either no charge or negative charge. So average will be partial negative. Delta means partial negative. There's negative charge, no charge, negative charge. So average, a partial negative charge. Same thing as this oxygen. So this is the real structure of this carbonate. The example is nitroethane. And this is the structure of a nitroethane. This is a nitro group. If you draw the detailed structure of a nitro group, will be a nitrogen with positive charge, connect with this oxygen with double bond, connect with this oxygen with using single bond, and this oxygen have a negative charge. So overall, it's a neutral because positive and negative charge will be cancelled. If you draw the resonance structure, follow the same rule. Lone pair of this oxygen push back. This nitrogen is sp2 hybrid, so it can accept the lone pair electrons. And at the same time, you have to break the pi bond to the oxygen. Okay, so nitrogen can not have more than 4 bonds here. And now, this is a resonance. Okay, so you can see this bond was single bond and then becomes double bond. And this bond was double bond. Now, after you draw the resonance structure, becomes single bond. So average, this bond will be about 1/2, right? So it's between single bond and double bond. Same thing, this bond will be between single bond, double bond. Okay, so, and this oxygen, no charge, but negative charge, negative 1 charge. So average is about 0.5 negative, right? So partial negative. Same thing, 50% negative charge here. So if you look at this, the hybrid, you can see the delocalization, negative charge delocalized between these two oxygen. Okay. Or you can say is distribute to these two oxygen. So that's called a delocalization. And this is more stable than usual. Okay. The example is this propionate. So this is a carbon anion. So with the triple bond here. And there's a lone pair here. This can push to here because this carbon is sp hybrid. So it can accept that electron. Again, this is the rule, right? So first, the lone pair of this electron push, and this carbon can accept that, but break this pi bond, and so you can form this resonance. This is more like a alene, but with a negative charge here. So the average of this bond, see, this is double bond, this is triple bond. So the average, it will be between double bond and triple bond. The other bond is single bond and double bond. Average between single bond and double bond. Okay, and this carbon, partial negative. This carbon also partial negative. So the negative charge delocalized to these two carbon atoms. So that's the real structure of this compound. Another example is cyanoethanide. So that is a carbon anion with a cyano group here. And look at this carbon has a lone pair, and this carbon is sp hybrid. So you can draw a resonance structure. So just push this lone pair electron back, form a pi bond. At the same time, break the pi bond here. So this sp hybrid carbon can accept. It's very similar with the last example. Okay, so you can form this resonance structure. Okay, and if you draw the hybrid, this bond is between double bond, single bond, and this bond is between double bond and triple bond. So that's why. And this nitrogen will be partial negative charge, and this carbon will be partial negative charge after average it. Okay, that's the real structure of this cyanoethanide. Let's look at the vinyl ether. Vinyl ether structure is shown here. So it's vinyl group, and it's a vinyl ethyl or ethyl vinyl ether. So, and the oxygen has lone pair here. Actually, has two lone pairs. So, and this carbon is sp2 hybrid. So we can draw the resonance. Follow the rule, right? And lone pair push back and push the pi bond to just one of the carbon, and then you can draw the resonance. Okay, so if you average this single bond, this double bond, so this will be 1/2, and this is double bond, a single bond, you can average, right? So it's a 1.5. So between single and double, and then this oxygen has positive charge. This has 0 charge. So average, partial positive. This carbon, no charge, but this is negative. So average, partial negative charge. Okay, now let's talk about the enolate. Enolate is the carbon anion on the alpha carbon of the carbonyl here. And to draw the resonance, follow the same principle here. So this lone pair can push back. This carbon is sp2, so it can accept. So it can break that pi bond to form this resonance. That's also enolate, it's called. It's a good nucleophile. And then if you draw the average, this bond is between single bond, double bond. This bond is also between double bond, single bond. And this oxygen will be partial negative. This carbon is also partial negative. So that's the real structure of this enolate. Okay, that's the hybrid. Let's talk about benzene. Benzene is a very famous aromatic compound. It's very stable. This is the benzene structure. Okay, 6 carbons. It's a ring structure with the 3 double bond here. And if you draw the resonance, follow the same rule. we can move the pi electron. Okay, the pi electron can push to here at the same time, push this pi electron to here, and at the same time push the pi electron here. So you can draw the other resonance. You can see all the double bonds switch the position, and that's a perfect example of delocalization. Average, you may notice that all the 6 bonds, they are all between single bond and double bond. So all the bonds are actually same. Okay, so that's the hybrid. Sometimes you see this kind of structure, that means same thing. That shows a big delocalization of the 6 pi electrons. Okay, that's benzene. Now let's look at the allylic carbocation. That's allylic carbocation. This is the allylic position. I show the example here. And then follow the same rule. We can move the pi electrons to here. And this carbon is a carbocation. It's sp2 hybrid, so it can accept that pi electrons. So you draw this just one arrow pushing to form this resonance. And this positive charge will formed because this carbon lost 1 electron after this pi electron pushed to here. And so that electron neutralized this positive charge here. So that's the resonance. And then the average, you will see this bond will be between double bond and a single bond. And this also between single bond, double bond. So you can draw this 1/2, 1/2. And then this carbon will be partial positive. This carbon is also partial positive after average. So that's the hybrid of this allylic carbocation. The positive charge distribute or delocalized to the 2 carbons here. Okay, let's talk about the benzylic carbocation. This is a little bit more complicated. You can draw a lot of more resonance structure. So benzylic position is here. That's benzylic position. If you have a carbocation, actually the pi electrons from the benzene can push, okay, follow the same rule, only the pi electron can do it. So now the pi electron push to here can draw this resonance. When this push to here, the pi electron neutralize this positive charge, but this carbon will lose 1 electron, so we'll have a positive charge here. That's the resonance, but not the only one. You can still keep going, so you can push this pi electron to here, and then form double bond here, and positive charge will be here. And then this pi electron can also push to here, and then you can form this resonance. Now positive charge will be here, and form this new pi bond here. And the last one is this pi electron can push back to here, and the positive charge will go back to the benzylic position here. You can draw 5 resonance. This is why the benzylic carbocation is very stable, because you have a much more delocalization energy here. Average, that's averaged. So you can see this bond, it's between single bond and double bond. And this 6 bond of the benzene, they all have between single and double bond property. So you can draw this as the averaged structure. But a positive charge can only delocalize to this carbon, or this carbon, or this carbon, or this carbon. You can see this carbon, or this carbon, or this carbon. Okay. So that's why you are only distributed to the 4 carbons, not all carbons in this structure. This is a benzylic carbocation. Another example is the phenolate. The phenolate is the conjugate base of the phenol. Okay, and based on the rule, and we can draw the lone pair of the oxygen push back and break this pi bond, and can draw the resonance structure. And then you can draw another one. We keep pushing this lone pair to here, form another pi bond here, and then we can break this pi bond. So you can draw the other resonance. Okay, you can notice the negative charge shifted from here to here and to here. Now keep going. So this can still push back to form the pi bond and break that pi bond. So form this resonance. The negative charge will be on here. And then this can still push back to form the pi bond and break that pi bond of the carbonyl. So form the fifth resonance structure. And this is very similar with benzylic. Now this is just the negative charge distribute to the 4 different atoms. Averaged, okay, this is average. First, the benzene is average, so all the carbon-carbon bonds are between single bond and double bond. And this carbon-oxygen bond is also between single and double bond. But the negative charge will be delocalized to this oxygen, and this carbon, and that carbon, if you look at that resonance. Okay, will never go to this carbon or that carbon or this carbon. So this is the hybrid of this phenolate. Because of this 5 resonance structure of the phenolate, so this phenolate is more stable than normal. So that's why the phenol's pKa is about a 10. It's much less than normal alcohol. It's more acidic. Okay, let's look at the cyclopentadienide. So this is a carbon anion on this 5-member ring, and with 2 double bond here. This is a very stable species. It's actually aromatic, similar with benzene. Now follow the same rule. We have a lone pair can push to here, and this carbon is sp2 carbon. Okay, so it can break the pi bond. Now you can form this resonance. And again, this can push back and then break that pi bond. You can notice that that's also sp2 carbon. And then you form this resonance. And this can keep going, can push back to form pi bond and break that pi bond. And then you can draw this resonance. And this can also push back, break that pi bond to form the 5th resonance. Now the average, all the 5 carbon-carbon bond, they will be between single bond, double bond, and all the 5 carbons will have a partial negative charge. So this negative charge will delocalize to all 5 carbons, 5 carbon atoms. Okay. So that's the average structure. Okay, so that's all the examples I would like to show you. So please let me know if you have any questions. Okay, good luck.